May 19th, 2026. California was hit by a violent earthquake, and what happened next has never been recorded in 170 years of monitoring this fault system. The aftershocks drove downward, getting stronger at 35 kilometers deep in a deep lithospheric rupture aimed directly at the root of the Garlock-San Andreas Intersection. Caltech's models failed. Don't go anywhere, because we are inside a 48-hour countdown that may determine whether 169 years of accumulated stress on the most dangerous fault crossing in North America finally breaks. Now, let's begin. May 19th, 2026, 4:47 in the morning, Pacific Time. The seismographs at the Southern California Seismic Network didn't just spike. They started drawing something that the analysts on the night shift had never seen in that exact shape before. Not a sharp jolt, followed by the familiar decay, that long, tapering tail of energy bleeding out, quieting down, returning to baseline. What they were watching was a sequence, a series of pulses arriving in waves, each one not smaller than the last, but comparable, in some cases, marginally stronger. The lines on their screens weren't relaxing, they were tightening. That was the first sign something was wrong. In Ridgecrest, people woke up and described it the same way, independently, without coordinating with each other. Not a sideways shake, not the familiar lateral violence of a strike-slip rupture rolling through the crust. This felt like pressure applied from beneath, like the ground itself was being pushed upward from a fist underground. A slow, sustained compression moving vertically through the floor, through the walls, through the chest. Residents in Mojave said their furniture didn't slide. It lifted slightly, then settled. People in Palmdale described a low-frequency vibration that felt more like standing next to a running industrial turbine than anything they associated with an earthquake. That sensation, vertical compression, rather than horizontal shaking, is not random testimony. It is a diagnostic signature. In seismology, the direction and character of ground motion at the surface tells you something precise about where the energy originated and how it traveled. Horizontal shaking dominated by S waves. The secondary shear waves is the fingerprint of a shallow, near-surface rupture. But a sustained vertical push, a sense of upward pressure, points to something deeper. Something where the wave geometry changes because the source is so far below that the angle of incidence at the surface is nearly perpendicular. The ground isn't being pushed sideways. It's being driven upward from below. This is what a deep source event feels like in your body. Now here is where the data stops being unsettling and starts being genuinely inexplicable. After any significant earthquake, aftershocks follow. This is not surprising. This is physics. The main rupture redistributes stress across the surrounding fault system, and smaller fractures release that redistributed stress in a cascade of diminishing events. The pattern is so consistent and so well documented that seismologists in 1917, a Japanese researcher named Fusakichi Omori, described it mathematically. The rate of aftershocks decays proportionally to the inverse of time elapsed since the main shock. More aftershocks early, fewer as time passes. The energy bleeds outward and upward, dissipating into the shallow crust, and the system gradually quiets. And critically, the aftershocks migrate. They move outward from the rupture zone, spreading horizontally, and they tend to become shallower over time as the stress field adjusts toward the surface. This is the standard behavior. This is what every model expects, what every dataset from the last century confirms, what every textbook describes. What happened after May 19th did none of that. The first aftershock registered at 18 kilometers depth, the second, 24 kilometers, then 31, then 35 kilometers below the surface of the Mojave Desert, deeper than the aftershocks that preceded it. not shallower. The migration vector wasn't outward and upward. It was straight down, like a drill bit finding its own path through rock, each successive event carving deeper into the earth rather than releasing upward toward open air. 35 kilometers. That number needs to sit with you for a moment. That is 35 kilometers straight down, not along the surface, not measured diagonally, but vertically beneath the point of rupture. That is deeper than the deepest point of the Grand Canyon times more than 10. That is approaching the boundary between the crust and the upper mantle, a geological frontier called the Mohorovičić discontinuity, the MOHO, where the composition and mechanical behavior of rock undergoes a fundamental transformation. And the intensity. This is the part that broke the models. When seismic energy propagates through rock, it attenuates. It loses amplitude. The deeper the source, the more material it has to travel through, and material absorbs energy. This is not a controversial claim. It is a foundational principle of wave physics, embedded in what seismologists call the Gutenberg-Richter relationship, which describes the statistical distribution of earthquake magnitudes and the rate at which energy decays with distance. Every data set in the historical record confirms it. As depth increases, the intensity of individual events in an aftershock sequence should decrease, not because there's less stress, but because the energy has further to travel, more resistance to overcome, more conversion into heat along the way. The aftershocks of May 19th were not obeying this relationship. At 35 kilometers depth, the events weren't weaker than those at 18 kilometers. They were comparable. One was slightly stronger. The decay curve that the Southern California Seismic Network's automated systems projected based on every previous aftershock sequence in the regional catalog was simply not matching the incoming data. The algorithms kept recalculating. The analysts kept staring at screens. One seismologist at Caltech, speaking on camera that evening, paused mid-sentence, looked down at his printout, and said, "This doesn't fit anything we have." That was the moment the scientific community understood this was not a routine event with an inconvenient data signature. This was something genuinely outside the boundary of what current models were built to explain. But to understand why the number 35 kilometers made an entire laboratory go silent, you first need to know what normal looks like in California. California sits on one of the most studied fault systems on the planet. Decades of seismographic networks, global positioning satellites, borehole sensors, and continuous monitoring have given scientists a detailed, high-resolution picture of how this landscape moves, where it stores stress, and how it releases it. There is a baseline here, a well-established one, and baselines matter because you cannot measure how far something has deviated until you know exactly where it started. Start with the San Andreas Fault, 1,300 kilometers long. That is the length of the entire state of California, measured coast to coast at its widest point, and the San Andreas runs nearly the full extent of it from the Salton Sea in the south to the coastal ranges north of San Francisco. It marks the boundary between two of the largest tectonic plates on Earth, the Pacific Plate to the west and the North American Plate to the east. These two plates are not colliding head-on. They are sliding past each other horizontally, in a motion geologists call strike-slip. The Pacific Plate moves northwest relative to North America at roughly 50 millimeters per year, about the rate your fingernails grow. Slow by human standards, relentless by geological ones. That motion is not smooth. Rock doesn't slide easily. The two plates lock together at their interface. Stress builds across decades and centuries. And then, when the accumulated strain exceeds the frictional strength of the rock, the fault ruptures. Meters of displacement in seconds. That is an earthquake. And along the San Andreas, the southern section in particular, the stress has been building since 1857. 169 years of accumulated strain because that is the last time this segment produced a major rupture. Now meet the second character in this story. The Garlock Fault runs east to west, nearly perpendicular to the San Andreas, cutting across the northern edge of the Mojave Desert for approximately 250 kilometers. Where the two faults meet near the town of Gorman, in the mountains north of Los Angeles, is the Garlock-San Andreas Intersection. This crossing point is the most mechanically complex zone in Southern California's fault network. Two major fault systems oriented at nearly 90 degrees to each other, both under accumulated stress, sharing a geographic node. The Garlock is generally described in the scientific literature as a sleeping fault. Not dead, the geological record shows it has produced earthquakes in the magnitude 7 to 8 range at various points in the prehistoric past, inferred from offset stream channels and dated fault trenches. But in the period of modern instrumental recording, it has been quiet. Occasional microseismicity, minimal creep, no major ruptures, compared to the San Andreas, which dominates the seismic conversation in California. The Garlock is the fault that researchers acknowledge, but don't lose sleep over. That characterization may need to be reconsidered. Now, the aftershock standard. What does normal actually look like after a significant earthquake in Southern California? After a major event, anything above magnitude 5.5. The aftershock sequence typically distributes across a depth range of 5 to 15 kilometers. Shallow. Concentrated in the brittle upper crust, which is the zone where rock is cold enough and stiff enough to fracture suddenly rather than deform plastically. These aftershocks spread outward from the main shock rupture zone, mapping the stress transfer onto neighboring fault segments. And they obey Omori's law with remarkable consistency. The rate decays. The magnitudes trend downward statistically, and within days to weeks, the sequence returns toward background levels. The critical structural parameter here is the brittle ductile transition zone. In the Southern California crust, this boundary sits at approximately 15 to 20 kilometers depth. Above it, brittle rock, capable of sudden fracture, capable of generating seismic waves. Below it, the rock is warm enough temperatures exceeding 300 to 400 degrees Celsius that it behaves plastically under stress. Instead of snapping, it flows. Instead of rupturing, it creeps. Stress that reaches this zone doesn't accumulate toward catastrophic release. It dissipates gradually, silently, absorbed by slow ductile deformation rather than explosive fracture. This is why the zone below 20 kilometers is seismically quiet in continental settings. Not because there is no stress, but because the rock cannot fail in the way that produces earthquakes. The physical mechanism for brittle fracture, the sudden loss of cohesion along a plane. The release of stored elastic energy as seismic waves requires rock that is cold enough and stiff enough to store that energy without flowing. Below 20 kilometers in the Southern California crust, those conditions are not supposed to exist. At 35 kilometers depth, by every parameter in the established baseline, brittle fracture is physically impossible. The rock down there is hot. It is under enormous confining pressure on the order of 10,000 to 12,000 atmospheres. It is in the ductile regime. It should be flowing, not shattering. And yet the seismographs said otherwise. The data from May 19th said that something, at 35 kilometers below the Mojave Desert, was breaking. That is the deviation. That is why the number matters. Not because 35 is large in an abstract sense, but because 35 is 15 kilometers past the boundary where fracture should be impossible, and the aftershocks weren't weakening as they descended. They were holding their intensity, which means the energy source wasn't dissipating. It was concentrated, focused, aimed. So what physics is operating at a depth where, by every rule we know, nothing is allowed to explode? Think of a candle. Not the flame the candle itself, the solid wax column, rigid and structured, capable of being snapped cleanly in two if you apply enough force suddenly. That snap, that brittle fracture, is exactly what an earthquake is at the mechanical level. Stress accumulates across a locked fault surface. The rock holds, 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 and then gives way all at once, releasing stored elastic energy as seismic waves that radiate outward in every direction. The upper crust, from 0 to roughly 20 kilometers depth, behaves like that candle. Cold enough, stiff enough, brittle enough to fracture suddenly rather than yield gradually. Now imagine the base of that candle sitting in a pool of warm wax, not liquid, not flowing freely, but soft, pliable, the kind of material that deforms slowly under pressure rather than snapping. Push on it and it bends. Stress applied to warm wax doesn't accumulate toward a catastrophic release point. It dissipates. The material absorbs the energy through slow plastic deformation, spreading it out over time and space, rather than storing it in the crystalline tension that precedes a rupture. Below 20 kilometers in the Southern California crust, rock behaves like that warm wax. The temperature is high enough, exceeding 300 to 400 degrees Celsius, that the mineral lattices within the rock begin to creep. Dislocations migrate through crystal structures. The material flows, imperceptibly slowly, but flows nonetheless. This is why the deep crust is seismically quiet in continental settings. Not silent because there's no stress. There is plenty of stress, but quiet because the material cannot store it in the form required for sudden fracture. The warm wax absorbs. The candle snaps. They are two different physical regimes separated by depth and temperature, and for more than a century of modern seismology, this division has held. The aftershocks of May 19th are operating in the warm wax, and they are getting stronger. That sentence should not be physically possible. If you are generating seismic energy in the ductile zone, the zone that is supposed to absorb stress, rather than amplify it, you are not dealing with residual release of the main shock's stress redistribution. You are dealing with something being actively injected from further below, an additional energy source. Something pumping stress into the base of the fault system rather than allowing it to bleed away. Two mechanisms can make warm wax behave like a candle. Both are known to science. Neither is comfortable to contemplate in this context. The first is supercritical fluids, at depths between 30 and 35 kilometers, under pressures ranging from 10,000 to 12,000 atmospheres. Water doesn't exist as liquid or vapor. It enters a supercritical state, a phase where the distinction between liquid and gas collapses entirely, and the fluid develops properties of both simultaneously. Supercritical water is extraordinarily mobile. It penetrates rock along grain boundaries and microfractures. And critically, it dramatically reduces the effective pressure holding rock grains together, what geologists call pore pressure. When pore pressure rises, the effective confining stress on the rock drops. And when confining stress drops, the frictional strength of the rock drops with it. Rock that should require enormous force to fracture suddenly becomes brittle at far lower stress levels. Supercritical fluids migrating through the deep crust can effectively convert ductile rock into brittle rock temporarily, locally, but catastrophically if the conditions align with an existing stress concentration. The second mechanism is dehydration embrittlement, specifically through a process called serpentinization. Certain minerals, particularly those found in mafic and ultramafic rocks from ancient oceanic crust that has been buried deep within continental lithosphere, contain water chemically bound within their crystal structures. When temperature and pressure reach critical thresholds, these minerals release that water. Serpentine breaks down. Amphibole dehydrates. The water liberated from these mineral transformations migrates upward through the surrounding rock, generating localized spikes in pore pressure, creating transient zones of brittleness in material that should be ductile. Here is the part that matters most. Both of these mechanisms don't just enable fracture at depth. They actively redirect stress upward. When supercritical fluids migrate through the lower crust, they follow pressure gradients, moving from high pressure at depth toward lower pressure in the shallower brittle zone. As they move, they carry mechanical energy with them. They effectively transmit stress from the deep ductile zone into the base of the brittle zone above, into the root of the fault system, into the exact zone where fracture is not only possible, but if the fault is already loaded with accumulated stress imminent. Dehydration embrittlement does the same thing through a different pathway. The water released from mineral breakdown generates a pressure pulse that propagates upward through the fault route. The Garlock fault has a route. Every fault does a zone where the surface expression of the fault tapers into the deep crust, transitioning from brittle rupture above to ductile shear below. That route is the mechanical anchor of the entire system. It is what holds the upper fault in its locked, stressed configuration, sustaining the stress that will eventually be released as an earthquake. The aftershock sequence of May 19th is currently aimed at the root of the Garlock fault. This is not an inference. The hypocenter migration. The spatial progression of aftershock locations with time traces a line from the main shock rupture zone directly toward the Garlock-San Andreas Intersection at depth. 35 kilometers, the base of the fault route, the anchor point of the entire system. And a deep source event carries dangers that a shallow earthquake does not. When a rupture originates at 35 kilometers rather than 10 kilometers, the seismic waves travel through more intact, less fractured rock before reaching the surface. Fractured, weathered shallow crust scatters and absorbs seismic energy. Deep, intact lithosphere transmits it with far less attenuation. The waves arrive at the surface, having lost less of their energy to the rock column they pass through, which means the ground motion at the surface is sustained over a broader area, with lower frequency components that travel further and penetrate larger structures more effectively. A shallow magnitude 6.5 shakes a limited region hard. A deep magnitude 6.5 shakes a much larger region less violently at the epicenter, but with energy that carries hundreds of kilometers and couples efficiently into the natural vibration frequencies of large buildings, bridges, and long-span infrastructure. But the deeper danger isn't the waves reaching the surface. It's what happens to the fault system when its root loses its anchor. And this is where the geological history of California speaks, because we have seen this scenario of a fault losing its root anchor before, and the consequences are something nobody wants to remember. January 9, 1857. The southern San Andreas Fault ruptured along nearly 360 kilometers of its length in a single event. The ground displaced by as much as 9 meters horizontally along segments near Fort Tejon. In the mountains north of Los Angeles, the shaking lasted nearly 2 minutes, an eternity for an earthquake. The Fort Tejon earthquake, estimated at magnitude 7.9, remains the largest historical earthquake in Southern California. The population of California at that moment was approximately 380,000 people. Most of them lived in San Francisco and the northern part of the state. The sparsely settled desert and mountain terrain near the rupture zone absorbed the disaster with relatively modest recorded casualties. The landscape took the hit that no populated city had to absorb. California's population today is 39 million. But what the Fort Tejon earthquake left in the geological record goes beyond the rupture itself. In fault trenches excavated across the Garlock-San Andreas Intersection, carefully dated sediment layers displaced by fault movement. Read like pages in a book, researchers found evidence that the Garlock Fault responded to the 1857 event. Stress transferred from the San Andreas rupture loaded the Garlock system. The geological stratigraphy suggests the Garlock experienced accelerated movement in the period following Fort Tejon, a mechanical response to the sudden redistribution of stress across the intersection. The two faults, crossing at nearly 90 degrees, are not independent systems. They are coupled. What happens to one reaches the other. This is the first line of historical testimony. October 16, 1999. The Hector Mine earthquake, magnitude 7.1. Ruptured in the Mojave Desert, geographically close to the Garlock's eastern segment. It was a large event by any measure, and it drew significant scientific attention at the time. But what the Hector Mine earthquake revealed about the Garlock Fault afterward was more significant than the earthquake itself. In the 3 years following the Hector Mine event, GPS sensors and creep meters installed along the Garlock Fault recorded something they had never recorded before: anomalous creep, slow, aseismic displacement movement along the fault surface that generated no detectable seismic waves, no felt shaking, no alerts. The Garlock was moving silently, not rupturing, but shifting. Researchers interpreted this behavior as a stress response, the fault system adjusting its internal stress distribution in response to the loading transferred from the Hector Mine rupture. The Garlock was not releasing stress, it was redistributing it, storing it in a new configuration. The phrase used in subsequent literature was cautious, but pointed the system appeared to be reloading. That reloading lasted 3 years. Then the Garlock went quiet again. The next entry in this record is the one that brought the Garlock into direct modern focus. July 4th and July 5th, 2019. The Ridgecrest earthquake sequence. A magnitude 6.44 shock followed within 34 hours by a magnitude 7.1 main shock, the largest earthquake in Southern California in 20 years. Ridgecrest sits in the Indian Wells Valley, directly adjacent to the western end of the Garlock Fault. The rupture zone of the July 5th main shock terminated less than a few kilometers from the Garlock's surface trace. What happened to the Garlock in the days and weeks following Ridgecrest was unprecedented in the instrumental record. The fault moved, not in an earthquake, in a slow slip event, aseismic creep, but at a rate and magnitude that no monitoring station had ever captured on the Garlock before. GPS measurements and satellite interferometry, specifically the synthetic aperture radar technique that measures ground deformation from space with millimeter scale precision, detected approximately 20 centimeters of displacement along a segment of the Garlock Fault. 20 centimeters. In a fault that had shown essentially no measurable surface movement in decades of continuous monitoring. The displacement occurred within weeks of the Ridgecrest sequence, was spatially correlated with the stress transfer pattern from the main shock, and bore no resemblance to anything in the Garlock's recent instrumental history. This was not modeling. This was measured. Satellites recorded it. Ground sensors confirmed it. 2019 established a direct, observationally verified precedent. The Garlock Fault responds to seismic stress input from the Mojave Desert. It does not ignore large nearby earthquakes. It moves, it loads, and when it moves in a slow slip mode rather than a rupture mode, the stress it accumulates doesn't dissipate, it waits. The pattern across these 3 events, 1857, 1999, 2019, tells a consistent story. Every time the Garlock-San Andreas Intersection receives significant stress input, the system requires either decades to redistribute that stress through slow aseismic processes, or it releases it through a rupture larger than the event that triggered it. There is no third outcome in the historical record. The intersection does not simply absorb and forget. It responds, and its responses have been getting more measurable, more instrumentally visible, with each successive perturbation. The May 19th event delivered stress input to that intersection from a depth and with a mechanism that none of the previous events matched. 1857 was a surface rupture. Hector Mine and Ridgecrest were shallow crustal events. What is happening now originates 35 kilometers deep, at the root of the fault system itself, in a zone that directly controls the mechanical behavior of everything above it. The historical record is not prediction, but it is not nothing. Every previous perturbation of this intersection left a mark. Some of those marks took years to fully express. Some expressed immediately. What they share is this: the Garlock-San Andreas Intersection has never received a stress input from its own root before. Not in any event we have instrumented, not in anything the geological record has been read to describe. History painted this picture, but what makes this time categorically different is what is happening simultaneously across the entire system, not just at a single point. The earthquake didn't arrive without warning. That's the part that matters. Not a warning in the way the public understands warnings, no alert on anyone's phone, no official bulletin, no press conference. The warning existed only in data streams that require trained eyes and calibrated instruments to read. And when you line those streams up side by side, when you place them against each other in chronological order, what you see is not a random collection of geological noise. What you see is a system preparing itself, quietly, methodically, over days and weeks before May 19th, 2026. Multiple independent monitoring networks recorded signals that, in isolation, each had a plausible mundane explanation. Together, they form something else entirely. Start with the ground itself moving before the earthquake happened. The continuously operating GPS network. A constellation of permanently installed, high-precision GPS receivers anchored into bedrock at sites across Southern California recorded anomalous horizontal displacement at stations near Palmdale and Lancaster beginning approximately 72 hours before the May 19th main shock. The displacement was not large by any casual standard, 2 to 3 millimeters, less than the width of a pencil. But GPS geodesy at this level of precision is not measuring casual movement. These stations are anchored in solid rock, shielded from thermal expansion effects, corrected for atmospheric delay, and capable of resolving motion at sub-millimeter scales over daily averages. 2 to 3 millimeters of horizontal displacement in 72 hours in a consistent direction at multiple stations, that is not instrument noise. That is the ground moving. And it moved before the earthquake, not after. This distinction is critical. Post-seismic displacement ground movement following an earthquake is expected. The crust adjusts to the new stress state, and GPS stations record that adjustment as gradual position changes in the days and weeks following a rupture. Pre-seismic displacement is a different animal entirely. Movement before the main shock means stress was already being released somewhere in the system. Silently, without generating the seismic waves that would register on standard monitoring networks. The technical term is aseismic slip, or slow slip event. A patch of fault surface that would normally be locked, storing elastic stress toward a future earthquake, instead begins to creep. Not fast enough to generate seismic waves detectable as earthquakes, just sliding, quietly, millimeters per day, releasing stress through a deformation rather than fracture. Slow slip events have been documented extensively along subduction zones, the Cascadia subduction zone in the Pacific Northwest being one of the best studied examples, but their role in continental strike slip fault systems like the San Andreas and Garlock is less well characterized. When GPS stations in the Palmdale-Lancaster corridor started moving 72 hours before May 19th, they were recording exactly this kind of silent slip. Somewhere beneath the Antelope Valley, a fault surface was beginning to move before anyone felt anything. That signal alone would have warranted attention, but it was not alone. 2 weeks before May 19th, the seismic monitoring network across the Garlock Fault region fell nearly silent. Not the regional network, Southern California, continued producing its usual background of small earthquakes. The constant low-level seismicity that characterizes any tectonically active zone. But the Garlock corridor specifically, which normally generates a steady trickle of micro-earthquakes below magnitude 2.0, the tiny stress relief events that bleed accumulated strain in small, continuous increments, went quiet. Near complete seismic quiescence across the fault zone for approximately 14 days. In seismology, silence is not reassurance. Silence is information. The small earthquakes that populate any active fault system serve a mechanical function. They are pressure release valves, minor fractures that allow accumulated stress to vent gradually rather than storing it toward a single large release. When those micro-events stop occurring on a fault that normally produces them consistently, the standard interpretation is not that the stress has gone away. The interpretation is that the fault has locked more completely than usual. The small release valves have closed. Stress is accumulating without the usual incremental bleeding, building toward a threshold that only a larger event can breach. 14 days of quiescence along the Garlock prior to May 19th. 14 days of stress accumulating without outlet. Then the third signal, and this one comes from water. Groundwater monitoring wells in the Mojave Desert region, maintained as part of California's water resource management infrastructure, not specifically as seismic monitoring tools, logged temperature anomalies in deep aquifer layers during the weeks preceding May 19th. The increases were modest, 0.3 to 0.5 degrees Celsius above seasonal baseline in wells accessing water at depths below 200 meters, small enough to be attributed to seasonal variation under normal circumstances. But the timing and the spatial distribution of the anomaly didn't match seasonal patterns. It tracked instead with the regional geology concentrated in areas overlying deeper structural features associated with the Garlock system. Temperature increases in deep groundwater can reflect changes in the geothermal heat flux from below, an indication that fluid circulation patterns in the deep crust are shifting. That warmer material, or thermally altered fluids from greater depth, are migrating upward through permeable pathways in the rock. This is precisely what you would expect if dehydration reactions were occurring at 30 to 35 kilometers depth, releasing chemically bound water from mineral structures and driving that water upward through the fault system. The thermal signal in the Mojave groundwater network may have been detecting, from the surface, the earliest expression of the deep lithospheric process that would eventually drive the anomalous aftershock sequence on May 19th. And then, 500 kilometers to the north, something else entirely. The same week that these signals were accumulating in Southern California, the Cascadia subduction zone, the offshore fault system running from Northern California to British Columbia, where the Juan de Fuca plate dives beneath North America, recorded a tremor episode. Not a large earthquake, not a megathrust event, a slow tremor, a diffuse, low-frequency seismic signal generated by fluid movement and a seismic slip along the subducting plate interface at depths between 25 and 45 kilometers. Cascadia tremors occur regularly and are monitored continuously. But this particular episode registered with slightly elevated amplitude compared to recent background activity. Cascadia is not connected to the San Andreas system by any direct fault linkage. The two systems are geologically distinct, driven by different plate boundary configurations. A tremor episode at Cascadia does not cause earthquakes in Southern California through any known mechanical pathway. But what both signals share is their source, the Pacific Plate. The same plate that grinds northwest past the North American plate along the San Andreas is the same plate that dives beneath North America at Cascadia. When that plate is adjusting its stress state at one boundary, the adjustment is not necessarily isolated to that location. The plate is a continuous rigid body. Stress changes propagate across it, not rapidly, not in ways we can currently model precisely. But the Pacific Plate stress state in May 2026 was not static. It was in motion at multiple boundaries simultaneously. Taken individually, Each of these 4 signals, the GPS displacement, the seismic quiescence, the groundwater temperature anomaly, and the Cascadia tremor, carries an innocent explanation. GPS signals fluctuate. Fault zones go quiet sometimes. Groundwater temperatures vary. Cascadia tremors are routine. No single signal, presented alone to a review panel, would have triggered a formal alert. But they didn't occur alone. They occurred together within the same 2-week window, across a system that was already being loaded by the deep lithospheric process we described earlier. Each signal pointing in the same direction, each one a different instrument reading from the same underlying machine. These isolated signals don't say much on their own, but once you understand the physical machine operating underneath, they suddenly form a picture that is far more complete and far more frightening. To understand what is actually driving this sequence, not just the aftershocks, not just the precursory signals, but the root cause of why this intersection is behaving the way it is right now, you need to go back roughly 30 million years and watch a piece of oceanic crust disappear. Before the San Andreas Fault existed in its current form, the western margin of North America was a subduction zone similar to what Cascadia is today. The Farallon Plate, a vast oceanic plate that once covered much of the eastern Pacific, was diving beneath the North American continent along its entire western edge. As the Farallon subducted, it carried with it the oceanic crust that had formed at the mid-ocean ridge dark, dense, mafic rock rich in minerals like olivine, pyroxene, and serpentine minerals that contain water locked within their crystal lattices. That subducted material didn't disappear. It was buried into the mantle, progressively heated and compressed as it descended, but fragments of it were also scraped off and accreted onto the base of the continental crust. The western margin of North America, at depth, is underlain by remnants of this ancient oceanic material, relict slabs, accreted fragments, mineralogically distinct from the overlying continental crust. That buried oceanic material is still there. At depths between 30 and 40 kilometers beneath the Mojave Desert and the transverse ranges, geophysical surveys, seismic reflection profiles, receiver function analyses, gravity anomaly maps indicate the presence of high-velocity, high-density material inconsistent with typical continental lower crust. This material is interpreted as fragments of the old Farallon oceanic crust, entombed in the lithosphere for tens of millions of years, and it is mineralogically primed for dehydration reactions at the temperatures and pressures that currently exist at those depths. Now place the fault system on top of this. The San Andreas Fault in Southern California does not run in a straight line between roughly the Salton Sea in the south and Parkfield in the north. It curves. Near the transverse ranges, the east-west trending mountain chain north of Los Angeles, the fault bends approximately 35 degrees away from the regional plate motion direction. This bend is called the Big Bend, and the Big Bend is not a passive geographic curiosity. It is a mechanical bottleneck of the first order. When two tectonic plates slide past each other along a straight fault, the motion is relatively pure strike-slip horizontal, parallel to the fault trace, with minimal compression or extension perpendicular to the fault plane. But when the fault bends, the plate motion direction and the fault orientation diverge. The Pacific Plate is still trying to move northwest. The fault, at the Big Bend, is oriented northwest-southeast. The mismatch between plate motion direction and fault geometry means that the sliding motion has a compressional component. The plates are not just sliding past each other, they are also being squeezed together at an angle. Geologists call this transpression, simultaneous strike-slip and compression acting on the same fault zone. The result, over geological time, is the transverse ranges themselves mountain ranges that have been squeezed upward by this compressional component. Some of the fastest rising mountains in North America, driven not by a collisional boundary, but by a bend in a transform fault. The San Gabriel Mountains, the San Bernardino Mountains. These peaks exist because the San Andreas curves, but the mechanical consequence of transpression extends far beyond mountain building. Transpressional stress fields are three-dimensional in a way that pure strike-slip fields are not. Stress is accumulating not just along the horizontal fault plane, but also vertically, as the crust is compressed and thickened. This creates a stress environment of exceptional complexity, not one dominant stress direction that a fault can resolve through a single clean rupture, but multiple competing stress components that load different fault orientations simultaneously. The Garlock Fault, oriented east-west, experiences the compressional component of San Andreas transpression differently than the San Andreas itself does. The intersection of these two fault systems sits precisely within the most mechanically congested volume of rock in Southern California. Into this already complex stress environment, now introduce the dehydration mechanism. At 30 to 35 kilometers depth beneath the Big Bend region, the temperature is approaching the threshold roughly 600 to 700 degrees Celsius, at which serpentine minerals in the buried Farallon material become thermally unstable. Serpentine contains approximately 13% water by weight, bound within its crystal structure. When serpentine breaks down a process called serpentinite dehydration, it releases that water into the surrounding rock as a pressure pulse. The reaction is not instantaneous and is not uniform. It progresses through the rock as temperature rises, liberating water at the reaction front, driving that water upward through whatever permeable pathways exist in the overlying crust. The fault zone itself is the most permeable pathway available. Water released at 35 kilometers depth finds the Garlock Fault route, the zone where the surface fault transitions into the ductile shear zone at depth and migrates upward along it. As it rises, it reduces effective normal stress on the fault surfaces it contacts. Rock that was locked by its own weight and confining pressure becomes less locked. The frictional resistance that was preventing slip decreases. And in a fault system already loaded to near failure by 169 years of tectonic stress accumulation since the 1857 Fort Tejon earthquake, a reduction in frictional resistance is not a minor adjustment. It is a key turning in a lock that was already under tension. This is the dehydration embrittlement mechanism operating not in a subduction zone, its classical setting, but in a continental intraplate fault system. It has been theorized, it has been modeled. What the May 19th aftershock sequence appears to represent is the first direct instrumental evidence of it operating in this geological context, in real time. Now, add the stress shadow. After the Fort Tejon earthquake of 1857, the rupture released an enormous quantity of stored elastic energy from the southern San Andreas system. That release didn't just reduce stress on the San Andreas itself, it altered the stress field across a broad region surrounding the rupture, creating zones of reduced stress called stress shadows. The Big Bend region, positioned adjacent to the rupture, fell within one of these shadows. For the subsequent century and a half, this reduced stress environment provided a measure of mechanical buffering. The region was carrying less tectonic load than it would have been without the 1857 release, making large earthquakes in that zone statistically less likely than they would otherwise be. Current geodetic data, GPS, velocity fields, strain rate measurements, in-SAR deformation maps indicate that the stress shadow from 1857 has been fully consumed. 169 years of tectonic loading has restored the stress field across the Big Bend to levels comparable to what existed before Fort Tejon. The buffer is gone. The protective shadow has been filled in by the relentless accumulation of plate motion stress. What that means, in plain terms, is that the Big Bend region is now as mechanically loaded as it was in the months before the largest earthquake in Southern California's recorded history. The Coulomb stress transfer model provides the final layer of this analysis. Every earthquake, by releasing stress in one location, redistributes that stress to the surrounding fault system. The redistribution follows the geometry of the fault network and the physics of elastic deformation. It is calculable, not random. Seismologists apply Coulomb failure stress models to estimate how stress from one earthquake changes the proximity to failure of neighboring faults. The calculation produces a value called delta Coulomb failure stress. Positive values indicate the target fault has been pushed closer to failure. Negative values indicate it has been pushed further away. When the May 19th event is entered into the Coulomb model, accounting for its source depth, rupture geometry, and focal mechanism, the results show positive delta Coulomb failure stress values loading both the eastern segment of the Garlock Fault and the southern San Andreas segment along Carrizo Plain. Both faults are being pushed closer to their failure threshold by the stress redistribution from May 19th, not marginally. The values at the current calculation are significant relative to the known stress deficit on those segments. A positive delta Coulomb failure stress means that fault is now closer to rupture than it was before May 19th. Not guaranteed to rupture, not imminent by definition, but closer, measurably, calculably closer. But a fault being pushed closer to its failure threshold doesn't guarantee rupture unless the systems start synchronizing with each other, crossing the point of no return. There is a concept in physics called the critical point. It applies to phase transitions, water turning to ice, magnetism switching direction in a metal, avalanches releasing from snowpack, but it applies equally to fault systems. And understanding it changes how you read everything that has happened since May 19th, 2026. A complex fault system is not a simple machine with a predictable breaking point. It is what physicists call a critical system, a network of interacting elements, each influencing the others, each capable of absorbing or transmitting stress depending on its local state. The behavior of such a system through most of its history is unremarkable. Stress accumulates, small events occur, energy bleeds out incrementally through micro-seismicity and aseismic creep. The system appears stable because it is continuously finding small local equilibria, venting just enough pressure through just enough small fractures to prevent any single stress concentration from reaching catastrophic levels. Think of a sand pile. You add grains one at a time. Most grains land, settle, and stay where they fall. Occasionally, a small avalanche occurs. A few grains cascade down a slope, redistributing locally, and the pile returns to apparent stability. The pile grows, grain after grain, avalanche after avalanche. The system manages itself. But the pile is also changing character as it grows. Its slopes are steeper. Its internal structure is more tightly packed. The grains are resting against each other at angles closer to their angle of repose. And then, not with any grain that looks different from the thousands before it. Not at any moment that announces itself, a single grain lands and the entire face of the pile collapses. That grain didn't cause the avalanche. The system was already at its critical point. The grain was just the last increment the system could absorb before it couldn't absorb anymore. The aftershocks drilling downward into the root of the Garlock-San Andreas Intersection are that grain. Each one individually transferable stress to a system already loaded to near capacity by 169 years of tectonic accumulation, stripped of its stress shadow buffer, and now being destabilized from below by deep lithospheric fluid migration. The question isn't whether any single aftershock matters. The question is whether the system is at its critical point, and the data from the 48 hours following May 19th is providing an answer that nobody in the seismological community is comfortable with. 24 hours after the main shock, analysts at the Southern California Seismic Network began noticing something in the aftershock timing that had no precedent in their catalog of comparable sequences. The aftershocks were arriving on a schedule. Not perfectly metronomic seismic events are never that clean, but with a regularity that statistical analysis confirmed was not random. Events of magnitude 2.0 and above were clustering in a temporal pattern with inter-event intervals consistently falling between 47 and 52 minutes. 47 to 52 minutes. Repeating for the first 24 hours of the sequence. Random processes don't do this. A truly random aftershock sequence, stress releasing wherever and whenever local conditions permit. Driven by the chaotic complexity of rock fracture at multiple scales, produces inter-event times that follow a specific statistical distribution, spread across many orders of magnitude, with no preferred interval. What the May 19th sequence was producing looked nothing like that distribution. It looked like resonance. Resonance is what happens when a system has a natural frequency, a preferred rate of oscillation, and external forcing aligns with that frequency. A child on a swing needs pushes timed to the swing's natural period to build amplitude. A wine glass shatters when sound matches its resonant frequency. A fault system resonating means that energy is not being released chaotically across the network, but is instead cycling building at one point, releasing at 47 to 52 minute intervals, then building again. The system is not venting, it is oscillating. And oscillating systems accumulate energy at their resonant nodes rather than dissipating it broadly. The resonant node in this case, the point where the oscillation is concentrating, is the Garlock fault route at 35 kilometers depth. Then came the Omori deviation. Fusakachi Omori's 1894 law has been validated against essentially every well-recorded aftershock sequence in the global catalog for over a century. The rate of aftershock occurrence decays in proportion to 1 divided by time elapsed since the main shock. Early in the sequence, aftershocks are frequent. As time passes, they become rarer. The decay is not linear. It follows the specific mathematical form of the inverse time function, but it is consistent, reliable, and robust across fault types, tectonic settings, and magnitude ranges. When seismologists fit an Omori curve to the early part of an aftershock sequence, they can project with reasonable confidence how the sequence will behave in the following days and weeks. The May 19th sequence stopped obeying Omori's law at approximately 30 hours post-main shock. The rate of aftershock occurrence, instead of continuing its expected decay, flattened. It plateaued. And then, between the 36th and 48th hour, it showed a slight but statistically significant uptick. The rate of events was increasing, not decreasing. The Omori curve projected downward. The actual data curved upward away from it. This pattern has a name. Seismologists call it the inverse Omori pattern, and it is one of the rarest and most studied anomalies in the observational record. It has been documented as a precursor signature in a small number of cases where a main shock was followed by a larger event rather than a decaying sequence. Not universally, there are inverse Omori patterns that resolved without escalation, but the statistical association between this pattern and subsequent larger ruptures is documented, peer-reviewed, and taken seriously by the community precisely because of what it implies mechanically. The system is not releasing stress faster than it is accumulating it. Stress is still arriving at the fault system faster than the aftershock sequence can vent it. The balance is running in the wrong direction. The B-value data confirms this from a different angle. The B-value is a parameter derived from the Gutenberg-Richter frequency-magnitude relationship. In any large catalog of earthquakes from a given region, the ratio of small earthquakes to large ones follows a consistent pattern for every unit increase in magnitude. The number of events decreases by a factor related to the B value. In Southern California's historical catalog, the B value is approximately 1.0. This means that for every earthquake above magnitude 4, you expect roughly 10 above magnitude 3, 100 above magnitude 2, and so on. The B value reflects the physical state of the fault system specifically, the heterogeneity of stress distribution. High B values indicate stress is distributed broadly, with many small events draining it across a wide area. Low B values indicate stress is concentrating fewer small events, more energy accumulating toward larger releases. Within the May 19th aftershock zone, the calculated B value for the sequence has dropped to between 0.6 and 0.7. This is a substantial deviation from the regional baseline of 1.0. In practical terms, it means the current fault system is producing proportionally fewer small earthquakes and proportionally more medium to large ones than normal California seismicity would predict. The stress is not spreading out and diffusing, it is concentrating. Pooling, the ratio of large events to small ones, is climbing, which in B-value terms is precisely what you observe when a fault system is approaching a critical failure state rather than recovering toward equilibrium. 4 independent signals: resonant inter-event timing, inverse Omori behavior, declining B-value, deepening hypocenter migration. Each one, individually, would warrant careful monitoring. Together, in the same sequence, over 48 hours. They are telling the same story from 4 different measurement frameworks. The system is synchronizing. It is not relaxing. The energy budget is not resolving toward stability. It is tilting toward a threshold. The system is synchronizing, but the critical question is whether human systems are capable of withstanding what that means, or whether our layers of defense are already thinner than we think. Every modern city rests on assumptions. Assumptions about infrastructure holding, about systems designed decades ago remaining adequate for conditions nobody fully anticipated, about warning systems buying enough time to matter. Southern California has built its earthquake preparedness narrative around these assumptions for 50 years. The shake alert system, retrofitted buildings, emergency protocols, the public messaging that says we are ready. The May 19th sequence is stress testing every one of those assumptions simultaneously. And what it is revealing, layer by layer, is that the margin between prepared and catastrophically unprepared is considerably thinner than the official narrative suggests. Begin with water. The Los Angeles Aqueduct is 113 years old. William Mulholland completed it in 1913, channeling water from the Owens Valley 230 miles south to a city that could not have grown without it. It remains, in 2026, a primary water supply artery for approximately 4 million residents of Los Angeles and surrounding communities. There is no realistic short-term alternative to it. The infrastructure that has been built around it, the treatment plants, the distribution networks, the storage reservoirs, assumes it functions. The aqueduct runs directly through the Garlock fault zone, not adjacent to it, not near it, through it. The pipeline crosses the Garlock surface, trace at multiple points along its route from the Owens Valley through the Mojave toward the San Fernando Valley. The crossing geometry means that any significant surface rupture along the Garlock, anything above magnitude 6.5, the threshold at which surface displacement along a strike-slip fault becomes probable, places the aqueduct at direct structural risk. Fault displacement of even 1 to 2 meters horizontally, which is modest for a magnitude 6.5 event, is sufficient to shear a pipeline not designed to accommodate lateral offset across its crossing point. The last major structural renovation of the Los Angeles Aqueduct's primary conduit sections was completed in the 1970s, over 50 years ago. The pipe sections crossing active fault zones have not been replaced with modern fault-tolerant designs, the kind that incorporate flexible joints and articulated segments specifically engineered to survive several meters of fault displacement without catastrophic failure. Those designs exist. They have been implemented in newer water infrastructure projects in Japan and New Zealand. They have not been applied to the century-old backbone of Los Angeles's water supply where it crosses the Garlock Fault. A Garlock rupture above magnitude 6.5 does not merely damage a pipe. It cuts the water supply to 4 million people with no timeline for restoration that anyone has credibly estimated at less than weeks. The energy picture carries its own arithmetic. The Mojave Desert has become, over the past 15 years, the backbone of Southern California's renewable energy transition. Solar farms stretching across hundreds of square miles of desert floor, wind installations along the mountain passes, high-voltage transmission corridors carrying that generated power south and west into the Los Angeles basin. The infrastructure concentration in the Mojave is not incidental. It is the deliberate result of California's energy policy, locating generation where land is cheap and sun is abundant, then transmitting the power to where people live. Those transmission corridors cross the same geological terrain as the aqueduct. The towers carrying high-voltage lines across the Mojave Desert are engineered to withstand ground shaking, but their design basis assumes a specific range of ground motion, intensity, and duration. A magnitude 6.5 or larger event centered on the western Garlock, with the deep source amplification characteristics of a lithospheric earthquake, could subject transmission tower foundations to ground motion, exceeding their design parameters, particularly in areas with softer sedimentary fill overlying the bedrock. Tower failures in high-voltage transmission lines produce cascading outages that propagate across interconnected grids faster than operators can manually isolate them. The disruption to Southern California's renewable generation capacity from a significant Garlock event has been estimated in internal utility planning documents at 30 to 40% of current renewable supply, potentially for weeks until transmission infrastructure is assessed and repaired. 4 million people without reliable water, 30 to 40% renewable power capacity offline. These are the infrastructure consequences of a Garlock rupture. But before any of that becomes survivable, people need warning. The Shake Alert Earthquake Early Warning System is California's most visible preparedness investment of the past decade. The system works by detecting the compressional P wave, the faster, lower amplitude wave that arrives before the damaging S wave shear motion, and using the seconds between P wave detection and S wave arrival to transmit alerts to phones, automated systems, and emergency infrastructure. Those seconds matter enormously. Enough warning to drop, cover, and hold. Enough for automated systems to halt trains, open fire station doors, slow surgical robots. The system has been publicly championed as California's technological defense against earthquake casualties. For shallow earthquakes, it works as advertised. A magnitude 6.5 event at 10 kilometers depth generates a P wave to S wave arrival time difference of roughly 15 to 30 seconds at distances of 50 to 100 kilometers from the epicenter, enough time for the alert to travel through the network, reach devices, and trigger protective responses before the damaging shaking arrives. For a deep source event at 35 kilometers, the geometry is different. The P wave and S wave both travel further to reach the surface, but the additional distance narrows their arrival time separation rather than expanding it. The angle at which both waves approach the surface from a deep source is steeper, meaning they take similar path lengths to complete their upward journey. The result, the time window between P wave detection and S wave arrival at the surface, for an event sourced at 35 kilometers, compresses to between 3 and 8 seconds. 3 to 8 seconds. Against a system designed to deliver 15 to 30, 3 seconds is not enough time for most people to register an alert, interpret it, and execute a protective response from whatever they are doing. It is enough time to be startled. In a high-rise building, it is not enough time for automated systems to complete safety protocols. On a freeway, it is not enough time for autonomous vehicle systems to safely decelerate. The deep source characteristic of the May 19th sequence, the same characteristic that makes it scientifically unprecedented, also partially blinds the warning system that Californians have been told will protect them. And then there is Antelope Valley. Palmdale and Lancaster together hold approximately 500,000 residents, making the Antelope Valley one of the fastest growing population centers in Southern California over the past 2 decades. Growth driven by housing affordability relative to central Los Angeles, by expanding commuter corridors, by the relocation of logistics and distribution facilities to the high desert. Much of this growth was rapid and occurred in areas that were not prioritized for seismic retrofitting programs focused on older urban building stock in Los Angeles proper. A significant fraction of residential construction in the Antelope Valley dates from the 1980s and 1990s, built after the initial post-1971 Sylmar earthquake code improvements, but before the more stringent requirements introduced following the 1994 Northridge earthquake, meaning these structures meet intermediate standards. Neither the oldest, most vulnerable construction nor the newest, most resilient. Palmdale and Lancaster sit directly above the western segment of the Garlock Fault, not near it, on it. The surface trace of the Garlock passes through the communities, beneath neighborhoods, under roads and utility corridors. A Garlock rupture initiating on its western segment produces maximum ground shaking precisely where 500,000 people live in structures of intermediate seismic resistance, served by water and power infrastructure of aging design, with a warning system that deep source events partially defeat. This is the complete picture of physical system under stress and a defensive system already thinner than we have been led to believe. But before we move to what comes next, I owe you complete honesty about what science actually knows and what science admits it doesn't. Let's clear the air before we go any further. Every major geological event triggers a parallel ecosystem of nonsense. It spreads faster than seismic waves, reaches more people than any monitoring network, and causes its own kind of damage not to buildings, but to the public's ability to think clearly about real risk. The May 19th sequence has already generated its share, so let's deal with it directly, briefly, and move on. HAAEEP, the High Frequency Active Auroral Research Program, a research facility in Alaska that studies the ionosphere using high-frequency radio waves. The claim that HAARP causes earthquakes surfaces after every significant seismic event, reliably, and it is wrong for a reason that requires no advanced physics to understand. HAARP operates by transmitting radio energy upward into the ionosphere, the electrically charged layer of the upper atmosphere, beginning at roughly 80 kilometers altitude and extending several hundred kilometers further up. Earthquakes originate in the lithosphere, the rigid outer shell of the Earth, extending from the surface down to approximately 100 kilometers depth, with the seismically active brittle zone concentrated in the uppermost 20 to 35 kilometers. The ionosphere and the lithosphere are separated by the entire column of the lower and middle atmosphere. There is no known physical mechanism by which radio frequency energy transmitted upward into the ionosphere could propagate downward through the atmosphere and into solid rock to induce fracture at 35 kilometers depth. The energy budget alone makes it impossible. HAARP's total transmitted power is measured in megawatts, while the energy released by even a moderate earthquake is measured in petajoules. The numbers differ by 9 orders of magnitude. HAARP did not cause the May 19th earthquake. Fracking induced seismicity from hydraulic fracturing is a real phenomenon, documented extensively in states like Oklahoma and Texas, where large volume wastewater injection has reactivated ancient fault systems, But California banned high-volume hydraulic fracturing in 2024, and no active fracking operations exist in the Mojave Desert region. More fundamentally, fracking-induced seismicity operates through a specific mechanism, pressurized fluid injection at shallow depths, reducing fault friction along pre-existing fractures, and it produces earthquakes at depths typically shallower than 5 kilometers. The May 19th sequence is centered at 35 kilometers. That depth is 7 times deeper than the deepest fracking-induced events in any documented case globally. Fracking cannot reach 35 kilometers. The mechanism doesn't operate there. The geology doesn't permit it. The government cover-up. This one deserves a different kind of answer. When Caltech scientists appeared on live television in the hours following May 19th and said, on camera, in their own words, that their models had failed, that the aftershock behavior was outside anything their predictive frameworks could explain. They were doing the opposite of concealing information. They were exposing, publicly and professionally, at some personal cost, the boundary of their own knowledge. Scientists don't do that when they're hiding something. They do it when the data is so anomalous that pretending otherwise would be indefensible. The Caltech statement was not a cover story. It was an admission that what is happening underground is genuinely beyond the current state of the science. That should be more alarming than any conspiracy theory, because it is true. Now, with that cleared away, let's talk about what the science actually cannot tell us, because these gaps are real, and they matter. Nobody in the world can predict exactly when an earthquake will occur. This is not a failure of effort or funding. It is a fundamental property of the physical system. Fault rupture is a threshold phenomenon in a chaotic mechanical environment. The stress state of the crust varies at scales too small to measure comprehensively. The frictional properties of fault surfaces vary at scales too fine to sample, and the triggering of rupture depends on conditions at the moment of failure that no monitoring network can resolve with sufficient precision. Japan has the densest seismic monitoring network on Earth. The 1995 Kobe earthquake and the 2011 Tohoku earthquake both occurred without specific advance warning from that network. The science of earthquake forecasting probabilistic statements about elevated risk over time windows is real and useful. The science of earthquake prediction, specific time, location, and magnitude does not yet exist in any operationally reliable form, and anyone claiming otherwise is not a seismologist. The dehydration embrittlement mechanism we have been discussing throughout this story is theoretically well-grounded, but observationally sparse in continental intraplate settings. The vast majority of empirical data on this process comes from subduction zone environments, the Cascadia subduction zone, the Japan Trench, the Chile margin, where oceanic crust carries water-bearing minerals into the mantle along well-characterized plate interfaces. Applying those models to an intraplate strike-slip fault system like the Garlock, where the buried oceanic material is ancient Farallon remnants rather than actively subducting crust, involves extrapolation across geological contexts that have not been directly compared. The theory says dehydration embrittlement should operate in this setting. The May 19th data is consistent with it operating, but the field data to calibrate the models precisely borehole measurements. Deep seismic reflection profiles specifically targeting this mechanism in this location does not exist at the resolution needed. The models are doing their best with incomplete inputs, and the Garlock fault's own behavior through geological time remains incompletely characterized. Approximately 170 years of modern instrumental and historical observation, the period since California became a U.S. state and basic record-keeping began, is a genuinely short window through which to observe a fault system whose recurrence interval for major ruptures may be measured in centuries or longer. Paleoseismic trenching has extended the record backwards several thousand years by reading displaced sediment layers, and those records suggest the Garlock ruptures infrequently but significantly. But the details of how the Garlock behaves in the decades preceding a major event, the slow slip patterns, the microseismic signatures, the stress interactions with the San Andreas are not well enough documented across multiple seismic cycles to allow confident pattern recognition. We are, in some sense, reading a book of which we have only seen the last few pages. Beyond these acknowledged scientific limits, there are two silent variables that could change everything about how this sequence evolves, and neither can be adequately constrained with current data. The first is blind fault geometry. The mapped fault network of Southern California, the San Andreas, the Garlock, the dozens of named secondary faults in the transverse ranges and Mojave represents only the faults that have been identified through surface expression, seismicity patterns, or geophysical surveys. Beneath the surface, particularly in areas covered by sedimentary fill that masks underlying bedrock structure, there are almost certainly additional fault segments that have not been mapped. The 1994 Northridge earthquake ruptured a previously unknown blind thrust fault beneath the San Fernando Valley, directly beneath Los Angeles. Nobody knew it was there until it broke. A blind fault situated between the Garlock and San Andreas systems in the mechanically complex zone of the Big Bend could either interrupt the stress transfer pathway we have been tracing, acting as a mechanical barrier that absorbs energy before it reaches the San Andreas, or amplify it, concentrating stress at a geometric irregularity and producing rupture at a location and on a timeline that no current models is tracking. The second silent variable is crustal moisture specifically. What decades of drought have done to the deep hydrological loading on Southern California's fault systems? Water stored in the crust, in aquifers, and saturated rock formations exerts weight. That weight, the hydrological load, contributes to the normal stress on underlying fault planes, affecting their frictional resistance to slip in ways that are calculable in principle, but rarely incorporated into operational fault models at the depth of the Garlock route. California has experienced severe drought conditions for extended periods over the past 2 decades, with significant depletion of groundwater aquifers, particularly in the Central Valley and Mojave regions. Reduced groundwater mass means reduced normal stress on underlying faults, a direction of change that, all else being equal, reduces frictional resistance to slip. How much this matters for a fault at 35 kilometers depth, where the primary confining pressure comes from rock overburden rather than groundwater, is genuinely uncertain. It may be negligible, it may not be. No current operational model for the Garlock-San Andreas system incorporates this variable at meaningful resolution. With what we know and what we don't know, here are the 2 paths that reality could take in the next 48 hours and the days beyond. This is the most probable single outcome. Say that clearly. Because it matters, the most likely result of the current sequence is that it resolves without a larger rupture. Seismology's historical record shows that the majority of anomalous aftershock sequences, even those that deviate from standard models, do not escalate to events larger than the main shock. The base rate favors resolution. Here is the specific mechanism by which that resolution could occur. The aftershocks currently drilling downward toward 35 kilometers depth are approaching a structural boundary. The lower lithosphere, the zone below the brittle ductile transition, below the fault route, approaching the thermal boundary layer of the asthenosphere, is not uniform. It contains compositional heterogeneities, ancient suture zones, and mechanical contrasts between different rock types that can act as barriers to stress propagation. If the deepening aftershock sequence encounters a sufficiently strong compositional barrier, a zone of material with different elastic properties that reflects or disperses the stress wave rather than transmitting it, the energy currently being focused toward the Garlock fault route would instead be distributed laterally, spread across a broader volume of the deep lithosphere, and dissipated through ductile deformation rather than concentrated fracture. When that happens, the observable signature changes in specific, measurable ways. The hypocenter depths stop descending and begin migrating back toward shallower levels, returning to the 15 to 20 kilometer range characteristic of normal crustal seismicity. Within 72 to 96 hours of that reversal, the inter-event timing loses its regularity. The 47 to 52-minute resonance pattern dissolves back into the random distribution expected from a decaying aftershock sequence. The rate of event occurrence begins following the Omori decay curve rather than deviating above it. The B value recovers toward 1.0 as the stress concentration at the fault root releases and redistributes. And most importantly, the creep meters and GPS stations along the Garlock fault surface trace show no additional anomalous displacement beyond the pre-seismic signal already recorded. If these 4 indicators all move in the right direction within the next 4 days, the May 19th sequence will be recorded as a resolved anomaly scientifically significant, operationally important as a case study, but not the trigger for a larger cascade. That outcome would be good news, but it would not be consequence-free news. Even in the false alarm scenario, May 19th has demonstrated something that the scientific and engineering communities cannot set aside and call irrelevant. The event showed that deep lithospheric rupture can occur in a continental intraplate fault system, not just at subduction zones, and that current predictive models are not built to handle it. When Caltech scientists say their models failed, they are not being self-deprecating. They are identifying a structural gap in the framework that the entire earthquake risk assessment industry uses to calculate hazard, design infrastructure, and set building codes. That gap existed before May 19th. The earthquake made it visible. Closing it will require years of research, new instrumentation at greater depths, and a willingness to revise probabilistic hazard models that current regulatory and insurance frameworks depend upon. And the infrastructure lesson does not wait for a larger earthquake to become relevant. A 113-year-old water pipeline crossing an active fault system is not an acceptable risk, regardless of whether any particular seismic sequence escalates. The aqueduct question, the transmission corridor question, the shake alert performance gap for deep source events. These vulnerabilities exist independently of what the Garlock does or doesn't do in the next 48 hours. The false alarm scenario doesn't make them less real. It just means there is more time to address them before they are tested by something larger. That is the best case, and I genuinely hope it is where we are headed. But my responsibility to you is to present the full picture of what the other scenario looks like. What happens if the aftershocks are doing exactly what the data is suggesting? This is not a prediction. Hold that clearly in your mind as you read what follows. What I am about to describe is a physical possibility, a sequence of events that the laws of mechanics permit, that historical precedent has partially demonstrated, and that current data does not rule out. The difference between a scenario and a prediction is the difference between a loaded gun on a table and a shot fired. The gun being loaded is a fact. Whether it fires depends on variables we cannot fully control or fully measure. What we can do is describe exactly what firing would look like, stage by stage, so that if it begins, you recognize it immediately. Stage 1 begins with the Garlock. The deep aftershock sequence has been doing one thing consistently since May 19th, 2026, pumping positive Coulomb failure stress into the root of the Garlock fault at 35 kilometers depth. Each event in the sequence, each brittle fracture in rock that should be too warm and too pressurized to fracture, transfers a small increment of stress upward along the fault route, nudging the lock sections of the Garlock closer to their failure threshold. At some point along that progression, If the stress accumulation continues rather than dissipating, the Garlock reaches the threshold it cannot hold. When the Garlock breaks, it breaks east to west. That is the fault's orientation. Its geometry forces any rupture to propagate along its roughly 250-kilometer length in the east-west direction, cutting across the Mojave Desert, perpendicular to the San Andreas. The rupture magnitude would likely fall between 6.5 and 7.2, depending on what length of the fault mobilizes in a single event. A magnitude 6.5 represents a rupture length of approximately 60 to 80 kilometers. A magnitude 7.2 represents a rupture extending most of the western Garlock segment. The ground motion in Antelope Valley would be severe. Palmdale and Lancaster, 500,000 people sitting directly above the western Garlock trace, would experience shaking of modified Mercalli intensity 8 to 9. At that intensity level, poorly constructed buildings suffer partial or complete structural failure. Well-constructed modern buildings sustain significant damage. The duration of strong shaking from a magnitude 6.5 to 7.2 event at shallow crustal depth would be 30 to 45 seconds long enough for cumulative structural damage to compound through multiple cycles of stress reversal in building frames and foundations. Within minutes of the rupture, 3 infrastructure systems would be at immediate risk. The Los Angeles Aqueduct, crossing the Garlock fault trace, would face displacement across its pipe sections at the fault crossing points, the same vulnerability described earlier, now actualized. The high-voltage transmission corridors carrying renewable power from the Mojave Desert toward Los Angeles would be subject to tower foundation movement and potential line failure along the rupture zone and Highway 14 and Interstate 15, the 2 primary road arteries connecting the Los Angeles Basin to the Antelope Valley, the Mojave Desert, and the inland regions beyond both cross-terrain directly affected by western Garlock rupture. Their closure, even temporarily, severs the surface transportation links between Los Angeles and its northeastern supply corridors at the moment when emergency response vehicles most urgently need to move in both directions. That is stage 1, severe, costly, survivable as an isolated event for a prepared region. But the Garlock does not exist in isolation. Stage 2 is where the arithmetic becomes catastrophic. When the Garlock ruptures, it does not merely shake the ground above it. It recalculates the stress field across the entire fault network surrounding it, and the fault most critically positioned to receive that stress recalculation is the southern San Andreas, specifically the Carrizo Plain segment. The Carrizo Plain section of the San Andreas Fault has not produced a major rupture since 1857. 169 years of Pacific plate motion accumulating at 50 millimeters per year, that is approximately 8.5 meters of accumulated slip deficit, stored as elastic strain in the locked fault interface? Waiting. The USGS's probabilistic seismic hazard models have consistently identified this segment as among the highest risk sections of the entire San Andreas system. It is not a question of whether it will rupture. It is a question of when and what triggers it. When the Garlock fails, it transfers positive Coulomb failure stress onto the southern San Andreas at Carrizo Plain. The transfer is not theoretical. It is calculable from the Garlock's rupture geometry and the elastic properties of the surrounding crust, and it loads precisely the segment of the San Andreas that is already closest to its failure threshold. If that additional loading arriving suddenly as a stress pulse, rather than the gradual tectonic accumulation of decades, is sufficient to push Carrizo Plain past its failure point, the southern San Andreas ruptures. The magnitude range for a full southern San Andreas rupture, from Carrizo Plain south through the San Bernardino and Coachella segments to the Salton Sea, spans 7.5 to 8.2. The USGS shakeout scenario. the most comprehensive modeling exercise ever conducted for a southern San Andreas event, used a magnitude 7.8 as its planning basis, a conservative estimate within the plausible range. The seismic wave field produced by this two-stage sequence, the Deep Lithospheric source from May 19th, the Garlock rupture, and then the San Andreas main shock would be unlike anything produced by any single event. The waves arrive at Los Angeles from different directions, at different times, carrying different frequency content. The deep source waves from the lithospheric sequence have already primed the ground with low-frequency energy. The Garlock adds energy from the northeast. The San Andreas delivers the dominant strike from the north and east simultaneously as the rupture propagates southward along its length at approximately 3 kilometers per second. The superposition of these wave trains creates a ground motion environment of exceptional complexity, not the clean single-source shaking that building codes and engineering models are designed around, but a multi-directional, multi-frequency assault on structures already stressed by the preceding Garlock event. This is particularly dangerous for tall buildings in downtown Los Angeles. High-rise structures anything above roughly 15 stories have natural vibration periods between 1 and 3 seconds. They sway at that rate when shaken. Seismic waves with similar periods, arriving with sufficient amplitude, drive those buildings into resonance, the same physical principle that can cause a bridge to oscillate destructively when soldiers march across it in step. The combined wave field from a two-stage Garlock-San Andreas sequence modeling suggests would contain sustained energy in precisely the 1 to 3 second period range, arriving at downtown Los Angeles for durations far exceeding what any single source event would produce. Buildings designed to the code would be tested at the extreme margins of their design envelope. Buildings with deferred maintenance, unaddressed retrofit deficiencies, or original construction predating modern codes would be tested well beyond it. Stage 3 does not wait for the shaking to stop. If the San Andreas rupture mobilizes its full southern length, the displacement at its southern end near the Salton Sea could transfer stress onto offshore fault systems in the Southern California Bight, including the Palos Verdes Fault, which runs along the seafloor off the Palos Verdes Peninsula. A sympathetic rupture of the Palos Verdes Fault, even at moderate magnitude, involves submarine fault displacement. Submarine fault displacement moves the water column above it. The result is a local tsunami, not a Pacific Basin crossing mega tsunami, but a wave with sufficient height and energy to affect the low-lying coastal areas of Santa Monica Bay within minutes of generation. Coastal Communities Venice, Santa Monica, Marina del Rey have evacuation plans that assume many minutes of warning and functional road infrastructure. After a magnitude 7.8 San Andreas event, road infrastructure in those communities may already be compromised before the wave signal arrives. Fire is the second cascade. Los Angeles has a dense network of natural gas distribution pipelines serving residential and commercial buildings throughout the basin. Earthquake shaking of sufficient intensity, particularly the sustained, complex ground motion of a multi-source event, ruptures gas lines at connection points, at corrosion sites, at locations where building movement separates pipe from fitting. Ignition sources are everywhere in a modern city. Electrical arcing from damaged wiring, pilot lights, open flames. In the hours following the 1906 San Francisco earthquake, fires started independently at multiple locations across the city and merged into a conflagration that ultimately destroyed more of San Francisco than the shaking itself. Los Angeles in 2026 has roughly 10 times the population of San Francisco in 1906, a gas distribution network orders of magnitude more extensive. And after years of drought vegetation in surrounding areas that is primed to carry fire, liquefaction adds the third layer. The Los Angeles River Basin, the filled coastal margins of Long Beach and Carson, the reclaimed land of Inglewood, and the areas surrounding the original course of Ballona Creek. These are zones where recent or artificial sedimentary fill, saturated with groundwater, loses its structural integrity when subjected to strong seismic shaking. Sand and silt particles, normally locked together by friction under the weight of overlying material, temporarily liquefy when seismic waves pump water pressure up through the sediment column faster than it can drain. Buildings sink, roads buckle. Underground utilities, water mains, sewer lines, gas pipes float upward or shear at depth. Recovery from liquefaction damage is measured in months, not days, because the damage is distributed across entire neighborhoods rather than concentrated in identifiable rupture lines. The USGS shakeout scenario for a magnitude 7.8 southern San Andreas rupture estimated 1,800 fatalities, 50,000 injuries, and $200 billion in direct economic losses. Those numbers, sobering as they are, assume a single source event with standard shallow crustal wave characteristics. They do not account for a preceding Garlock rupture that has already damaged infrastructure and reduced the capacity of the response system. They do not account for the enhanced ground motion complexity of a multi-source sequence, and they do not account for the deep source wave field that the May 19th sequence has been generating for 48 hours before either fault surface rupture occurs. This is not a prediction. This is the range of what physics permits. And to know which scenario we are moving toward, here are the specific signals that you and I need to watch in the days ahead. No prediction. That commitment stands from the beginning of this story, and it stands here at the end. What follows is not speculation about what will happen. It is a precise framework for what to observe, what specific thresholds matter, and how to interpret what the data is telling you over the next 2 to 4 weeks. If you live in Southern California, this is the most practically useful thing in this entire video. If you live anywhere else, it is a template for how to think about any geological hazard unfolding in real time. 5 signals, each one independent, each one measuring a different part of the system. Watch all 5 simultaneously, because no single signal tells the complete story. The first signal is aftershock depth. Open the Southern California Seismic Network Earthquake Catalog, available at the network's public website, updated in near real time, free to access without any technical background. Filter for events of magnitude 2.0 and above in the region surrounding the May 19th rupture zone. If, after 72 hours from May 19th, the depths of those events are still predominantly clustering below 25 kilometers, still in the deep lithospheric zone, the system has not returned to normal crustal behavior. The key threshold is 25 kilometers. Events consistently shallower than that, trending toward 15 to 20 kilometers, indicate the sequence is migrating back into the standard brittle zone and potentially resolving. Events staying deep or deepening further indicate the lithospheric process is still active. This is the single most important indicator in the current sequence, and it is the one you can monitor yourself without any specialized training. The second signal is the ratio of larger to smaller events in the aftershock catalog, a proxy for the B-value that doesn't require statistical software to track. Count the number of events above magnitude 3.0 and compare it to the number of events above magnitude 2.0 in any given 24-hour period. In a normal, resolving aftershock sequence with a B-value near 1.0, you expect roughly 10 magnitude 2.0 events for every 1 magnitude 3.0 event. If that ratio shifts, if you are seeing proportionally more magnitude 3.0 events relative to magnitude 2.0 events, the B-value is declining, meaning stress is concentrating rather than dispersing. A ratio of 5:1 or lower sustained over multiple days is a red flag that professionals will be noting regardless of whether it is publicly communicated immediately. The third signal is Garlock fault creep. The USGS maintains a network of creep meters along active fault segments in California instruments that measure fault surface displacement at millimeter to sub-millimeter resolution across short baselines anchored in the fault zone. Creep meter data from the Garlock network is not always immediately publicly accessible in raw form, but significant creep events generate detectable signals in the GPS network that are publicly available. If the Garlock fault begins displacing at rates exceeding 5 millimeters per week sustained, directional displacement in the GPS time series at Palmdale and Lancaster stations, that is the surface expression of the fault root loading that this sequence has been tracking. 5 millimeters per week sounds small. On the Garlock, which has been effectively locked for most of the modern instrumental record, it is not small. It is the fault waking up, and it deserves immediate attention from anyone living in the Antelope Valley. The fourth signal is the GPS velocity field across the broader Palmdale-Lancaster region. The continuously operating GPS network stations in this area measure three-dimensional ground position daily. What you are looking for is not the pre-seismic slow slip that preceded May 19th. That signal has now been incorporated into the post-seismic baseline. What to watch for next is a renewed episode of anomalous horizontal displacement in a consistent direction, exceeding 5 millimeters per week. That is not explained by the post-seismic relaxation following the May 19th main shock. Post-seismic relaxation is real. The crust continues to adjust elastically for weeks to months after any significant earthquake. But it decays with time and follows predictable spatial patterns. A new accelerating signal, or a signal inconsistent with the expected post-seismic pattern, means new deformation is occurring. New deformation means the fault system is being actively driven, not passively recovering. The fifth signal is the official probability assessment from Caltech and the USGS. Both institutions publish operational earthquake forecasts for California through the USGS Earthquake Hazards Program. The current background probability of a magnitude 6.5 or larger earthquake occurring within 30 days, anywhere in the Southern California region, is approximately 0.3%, 3 in 1,000. That is the baseline, the noise floor of California's seismic hazard. If Caltech or the USGS updates their operational forecast for the southern Garlock-San Andreas region, specifically to a probability exceeding 5%, for magnitude 6.5 or larger within 30 days, a threshold more than 15 times above background, that is not a routine update. That is these institutions telling you, in the most careful and legally considered language available to them, that they are genuinely concerned. They will not use those words. They will publish a number. The number will tell you what the words cannot. Now, the last thing I want to say to you, not every person watching this lives in Southern California, but every person watching this lives somewhere on a planet with active geology, aging infrastructure, and monitoring systems that are better than they were 50 years ago, but still incomplete. The lesson of May 19th is not specific to California. The lesson is that systems we believe we understand can produce behaviors that fall outside the models we built to describe them, and when that happens, the gap between preparation and unpreparedness becomes the difference that matters. If you live in Southern California right now, check your emergency kit. 4 liters of water per person per day. For a minimum of 3 days, that is 12 liters per person. Stored and accessible. Non-perishable food for the same window. Any prescription medications your household depends on, with enough supply to manage a week of disrupted pharmacy access. A battery-powered radio, because cellular networks fail under demand load after major earthquakes, and a radio requires no infrastructure to receive. Portable battery banks for phones. Copies of critical documents stored somewhere other than your phone. Know where your gas shutoff valve is. Know where your water main shutoff is. Know where your electrical panel is and which breaker controls which circuit. These are 10-minute pieces of knowledge that you will not have time to acquire after an earthquake when you can smell gas and your hands are shaking. Identify a meeting point for your household. A specific location where everyone goes if communication is impossible. Choose a contact person outside California who family members can call to relay information to each other, because long-distance calls often complete when local calls cannot in the minutes following a major event. For information after any significant earthquake, go to the USGS Earthquake Hazards Program, the California Governor's Office of Emergency Services, and the Southern California Seismic Network, not social media, not news aggregators that are recycling social media. The primary sources, which update their data continuously and do not have an incentive to amplify uncertainty into alarm. And if you are a renter or homeowner in Southern California, find out when your building was constructed and under which edition of the California Building Code. Buildings constructed before 1971, before the Sylmar earthquake, forced a major revision to seismic code requirements, carry the highest structural risk in a large event. Buildings constructed between 1971 and 1994, before Northridge forced another significant update, occupy an intermediate risk category. Buildings constructed under post-1994 codes, and especially those built after 2010, carry the lowest risk. This information is public record, available through your county assessor's office. It takes 15 minutes to look up. It may be the most consequential 15 minutes you spend this week. We don't know what tomorrow looks like, but we can choose how we face that uncertainty with preparation, with knowledge, and with clear eyes. If you made it this far, thank you. Genuinely. This wasn't light viewing, and the fact that you stayed says something real about you. Where are you watching from right now, California? Or somewhere else entirely? Drop it in the comments and tell me what you want me to go deeper on next: the Shake Alert System, the full history of the big one, or how to actually survive a major earthquake in a modern city. If tonight made you curious about how the San Andreas truly works at the tectonic level, that video is linked right here. And Tokyo, why it keeps standing while other cities collapse, that one is coming next. I'll be tracking this aftershock sequence and updating you the moment new data matters. Turn on notifications. See you.